So in order to elaborate on all of that, Michael, I want to ask you a simple question. And here it is. What makes reinforcement learning hard?
I'm going to say living on the streets.
Makes reinforcement learning hard?
Yeah, it sort of hardens it.
Let me ask that question slightly differently.
Oh, okay.
From a computational point of view, from an algorithmic point of view, what makes reinforcement learning hard?
So, well, there's a lot of things we've been talking about. There's the notion of delayed reward is a very tricky thing.
Oh, I like that one. Yeah, I like that one enough. I'm going to write it down.
You're not going to wait?
No, I'm not going to wait. I'm just going to write it down right now because it's ironic that way.
And a related issue, well, there's two pieces of that. There's the delay and there's a reward. The reward part is like, unlike, say, supervised learning, reinforcement learning is trying to do its job based on very weak feedback. It's only told how it's doing and not necessarily what it should be doing.
Right, which makes it very different from normal function approximation in the way that we think about it in supervised learning. Okay, what else?
If we do try to use something like supervised learning, one thing that makes the function approximation hard is the idea that it's kind of a moving target. We tend to base our estimates on our current estimates as opposed to anything kind of legitimately valid in the world.
Right, so doing estimates based on estimates is a lot like averaging averages.
Okay. I want to say bootstrapping is the issue.
Yeah, I agree with that. Bootstrapping is sort of a problem. I think I would probably summarize that as the problem with the need to do good exploration. And that's a little different from the normal supervised learning setup where you've got a bunch of training examples. Here, because you only have estimates in the reinforcement learning context, you have to do a bunch of extra things to actually figure out how to get good estimates so that you can actually do good learning. So one more thing, I think, sort of worth mentioning, that makes this sort of hard, and it's kind of very basic kind of computational problems, right? You know, when we describe computational complexity, we talk about it in terms of big O, and the question is big O of what? So what's the what here? What's the in our big O that makes R hard?
Well, there's a lot of them.
Like what?
Well, I mean, if we're thinking about sort of MDP style reinforcement learning, then the size of the state space is a big O.
Mm-hmm.
The size of the temporal window in some sense, like how delayed is the reward.
Mm-hmm.
There's issues on, well, it could be the actions as well. There's lots of things that could scale. But I guess what makes state super hard is that you can very easily specify a problem that has a state space with an exponential number of states that is still relatively simple, but algorithms that don't generalize between states are not going to be able to learn in them very effectively.
I think all of what you said is true. Some of it, I think, is kind of captured, though not necessarily explicitly in the first two bullet points. But I'd like to focus on states and actions. That the problem is that the learning that we need to do grows superlinearly in general. We aren't very, very careful and smart in the number of states and the number of actions. And so we really need to have kind of clever ways of thinking about learning across multiple states and perhaps multiple actions. And in fact, when you talked about function approximation and generalization, I would claim that, at least in sort of this discussion, we could talk about that as a way of dealing with generalizing over states, that you did function approximation over value functions, right? So here you tried one way of dealing with the problem of scale when it comes to states is, well, if I learn something about one state, I want to somehow have that teach me something about a bunch of other states. And then I won't have to visit every single state, an infinite number of times and take every action an infinite number of times. And that's really good. That's really important, right? And the trick here is I can see many, many states by just seeing a single state. And that's what function approximation over the value functions actually gives me. Agreed?
Yeah, I don't know that I would say it quite that way, but that we learn about many states when we learn about other states or something like that. But that's absolutely the way I was thinking about function approximation, is helping us to kind of fill in the gaps for states that we haven't visited nearly as often.
So, in fact, I could be aggressive and ask you the question, why did you do all this function approximation over states, but you didn't do any function approximation over actions, Michael?
That would be aggressive. I don't have a wonderful answer to that. I mean, it's tradition in the sense that a lot of the MDPs that people have been working with really do try to keep the action space relatively small and expand in the state space, but that's not really that good of an answer. I think large action spaces are really important too. We just don't have as good ways to deal with them. For one thing, the computing the max ends up being hard in Q learning.
Right. So, in fact, what I'm going to try to talk about in the rest of the lesson is trying to do generalizations of the sort of generalization that you were talking about, and think about how we can learn about actions and how we can abstract over actions in the same way that you were abstracting over states.
Oh, that seems great and a little bit meta.
A little bit meta. And so that's why the lesson's generalizing over generalizing. And the whole point in the end, I'm going to claim, other than just sort of it's interesting in and of itself, is that it's going to allow us to scale. So all of these tricks ultimately have a kind of practical use, including function approximation, of allowing us to scale.